Hello and welcome to another video. In today's video, we will be talking about distance versus time graphs and how we can analyze them to understand more about the motion of an object. So first, what is a distance versus time graph? On the right-hand side of the screen, you can see an example of one. A distance versus time graph is a graph that shows how an object's distance, also known as position, changes over the course of time. The most important part of a distance versus time graph is the slope of the line. The slope of the line on a distance versus time graph tells us the velocity of the object. So as we continue to learn about how to analyze distance versus time graphs, keep in your mind that what we're looking at is the slope of the graph, and what that is going to tell us is about the object's velocity. Before we finally start looking at distance versus time graphs and analyzing them, let's have a quick little math review. So I told you that slope is the most important part of a distance versus time graph and that it tells us the velocity of the object being graphed. So as a quick review from math class, we should remember that slope, also known as m, is the value that describes the steepness of a line. We know that slope is the change in y, or the vertical value, over the change in x. Here I can see the change in y, and I can see the change in the x value. That is what gives me the slope, or the steepness of my line. You should know that the formula for calculating slope is y2 minus y1 over x2 minus x1. That means that you select any 2 points along the line. You select one as point 1 and the other as point 2, and you plug in their corresponding y values and subtract them in the numerator, and you plug in their corresponding x values and subtract them in the denominator. You can see an example of that being done here on the screen. Finally, you may also have heard slope referred to as rise over run. This is a nice, helpful mnemonic device to help us remember what should be in our numerator and what should be in our denominator, or what we should look at on the graph to find the slope. This is the rise, or the vertical y value, over the run, or the horizontal x value. Now that we know what slope is, we're going to start by looking at all of the potential slopes that we can see on distance versus time graphs and what they tell us about the motion of the object. The first potential type of slope that we can see on a distance versus time graph is a slope of 0. You should hopefully remember from math class that a line with a 0 slope is just a horizontal line. That is because there is no change in the y value, so if you were to plug that into my slope formula, you would get m equals to 0. What this means on a distance versus time graph is that as time goes on, the distance of the object is not changing. If we apply that to what we know about motion of objects, an object whose distance is not changing over time is an object that is at rest, or with a velocity of 0. So anytime I see a horizontal line, I know that is a 0 slope, and I know that slope tells me velocity. So if my slope is 0, the velocity of the object is 0, meaning that the object is at rest or is not moving. An example of an object that would have a horizontal line or a 0 slope on its distance versus time graph is a helicopter parked on a helipad, meaning its distance is not changing, it is at rest, its velocity is 0. The second type of slope that we can see on a distance versus time graph is a positive slope. Positive slope means a line pointing in the positive direction. That means that distance is changing positively and time is changing positively as well. You can see 2 examples of lines with positive slopes here on my graph. This means that m is a positive value, and this tells me that the distance is changing positively over time. What does that mean? This means that the object is moving in the positive direction or away from the origin. This means that the starting point of my distance is here at the origin, and the object is moving away from it. Point of note, and you should probably write this down in your notes. Lots of people look at this line and think, hey, that's pointing upward. That object must be speeding up. In fact, that is not true, and that is not what a positive slope tells me. So don't fall for the trick of seeing that positive slope and stating that that means the object is speeding up. Remember that a positive slope just tells me that the object is moving in the positive direction or away from the origin. An example of this would be a runner starting at the starting line and moving away from the starting line over time. Next, and very similar to the one we've seen previously, but the opposite, we can see a graph with a negative slope. This means that time is changing in the positive direction, but the distance is changing negatively, meaning that the line is pointing downwards or in the negative direction. This means that if I were to calculate my slope, I would get a negative value. This tells me that the distance is changing negatively over time. This tells me that the object is moving in the negative direction or back toward the origin. Just like I said in our previous graph, don't fall for the trick that this line means the object is slowing down. It doesn't, it just means that it's moving in a negative direction or back toward the origin. An example of this would be our runner who had left the starting line, made it to the finish line, but then came back. If I were to graph his motion from the finish line back to the starting line, I would see a negative slope showing me that he is running back to the starting line or towards the origin. Another type of slope that we should be able to recognize is a constant slope. We just saw two examples of constant slope. In fact, all three of the examples that we've looked at so far have been constant slopes. I know that the slope is constant because my lines are linear, meaning they are not curved. That means the steepness of the line is the same for the entire length of the line. That's how I know that I have a constant slope. A constant slope tells me that the distance of the object is changing at the same rate, or distance is changing the same amount per each unit of time. This means that the object's velocity is constant. So if you think back to the examples of positive slope and negative slope, I told you don't fall for the trick that this means the object is slowing down and this means it's speeding up. Now we know that the constant slope, or the straight line, tells me that the velocity, or the speed of the object, is staying the same. So here I see a constant negative slope, here I see a constant positive slope, and here I see yet another example of a constant slope, which happens to be 0. This means that in all three examples, the velocity of the object is constant, meaning its speed is not changing. An example of this would be a car driving down the highway with cruise control set on 65 miles an hour. This means that the velocity of the car will stay at 65 miles an hour or will stay constant. That means that I will see the same slope for the entire length of the line unless and until the velocity of the car changes. Now that we know what a constant slope tells us, we can probably assume that a non-constant slope, which means the line is curved or not linear, tells me that the slope is changing over the length of the line. I can see a very shallow slope here that starts to get very, very steep at the end, and then the direct opposite here. This tells me that the object's distance is not changing at the same rate, which tells me that if I see a non-constant slope or a curved line, I know that the object's velocity is not constant or it is changing, and based on our definition of acceleration, we know that that tells me that the object is accelerating. So a curved line tells me non-constant slope, tells me velocity is non-constant, which tells me that the object is accelerating. Let's look at the first example, an example of an increasing slope. So an increasing slope is a curved line where the slope is steeper at the end than at the beginning. That means that the slope is greater at the end of the line than it is at the beginning. This tells me, first, that the object's velocity is non-constant, but more specifically, it tells me that the object's velocity is increasing. A lower slope to a larger slope tells me that velocity is increasing, which we know is a form of positive acceleration or speeding up. An example of this would be a car speeding up or positively accelerating as it drives down the highway. I would see a less steep slope at the beginning of the line, increasing to a much steeper slope towards the end of the line. On the other hand, I can see a non-constant slope, which is decreasing. Of course, I know if the slope is non-constant, it will be a curved line. In this case, I will have a steeper slope at the beginning to a less steep slope at the end. This tells me that the object's velocity is non-constant, but that it is decreasing. This means that the object is negatively accelerating or slowing down. Initial slope, very steep. Final slope, less steep, tells me that we have a negative change in velocity, which is negative acceleration or slowing down.